Approximation crawled. Bisection halved the gap each step. Now meet the fastest of them all. To find the square root of a number, Newton-Raphson takes just a handful of guesses. The catch: it only finds square roots. Let's see how it slides down a tangent line to the answer. Newton-Raphson finds roots of a polynomial. Take a polynomial like ax squared plus bx plus c, or a higher degree one. Start with any guess you like, then compute a better one. The new guess is the old guess minus the polynomial evaluated at that guess, divided by the derivative evaluated at that same guess. In other words, replace x with your guess in both the polynomial and its derivative, and the value drops out. How does a root finder give us a square root? Here's the trick. Finding the square root of 24 means finding the s where x squared minus 24 equals 0. Set x squared minus 24 to 0, and x squared equals 24, so x is the square root of 24. So to get the square root of any value k, we just hand Newton-Raphson the polynomial x squared minus k. Now specialize the rule. Our polynomial is x squared minus k, so f of the guess is the guess squared minus k. The derivative of x squared minus k is 2x, so f prime of the guess is 2 times the guess. Drop both into the update rule. The better guess equals the current guess, minus the quantity guess squared minus k, divided by 2 times the guess. That single line is the whole method. Here's the geometry behind that formula. Plot f of x equals x squared minus 24. Its root, where the curve crosses the x-axis, is the square root of 24. Start at a guess, say 12. Go up to the curve, then draw the tangent line there and follow it down to where it hits the x-axis. That landing point is your next guess, 7. Repeat, up to the curve, down the tangent, and each landing sits closer to the true root. The code is even shorter than bisection. We want the square root of 24 within 0.01. Pick a starting guess. A reasonable one is k divided by 2, so just half the number. Keep a count of guesses. The loop condition matches bisection exactly. While the absolute value of guess squared minus k is bigger than epsilon, keep going. Inside, bump the counter, then make the new guess with the Newton-Raphson line. That one line is f of guess over f prime of guess. Let's run it for k equals 24. The starting guess is 12. Guess squared minus k is 120. Way outside epsilon, so we update. 12 minus 120 over 24 gives 7. 7 squared minus 24 is 25, still too big. Update again, and the guess becomes about 5.21. Now its square is off by roughly 3.19. One more step lands near 4.91, off by under 0.1. The fourth guess reaches 4.899 within 0.01. 4 guesses, and the square root of 24 is about 4.9. Try a big one, 54,321. Newton-Raphson finds its square root in just 10 guesses, an answer as good as bisection or the long approximation, far faster. Why start at k over 2? No deep reason, it's just a convenient value tied to k. 100 will work too because the method converges regardless. The trade-off: this is a limiting algorithm. It only finds square roots. It can search a room for a person or anything outside this one problem. Step back. Every method we've seen is really one idea. Guess and check. We guess a value and check whether it's right or within epsilon of right. And each shares the same 3 parts. First, a loop, something to repeat. Second, a way to generate the next guess. This is where the algorithms differ from one another. Third, a way to check the guess against epsilon and to keep going if it's not close enough yet. Same skeleton, different guessing strategy. Line up the 4 we've met. Exhaustive enumeration checks every value in a set. Because it's exhaustive, you know exactly how many steps it takes. Approximation works in small increments, good for square roots, cube roots, any approximation problem. Bisection search beats approximation, but only when the space has an ordering and you can tell whether a guess is too high or too low. Without those, you can't use it. And the Newton-Raphson is the fastest here, but the narrowest, square roots only. Each one is guess and check. They differ in how they generate the next guess. That wraps up search. We've learned to write a lot of code, expressions, variables, conditionals, and loops. Enough control flow to build real algorithms. But two big ideas in every modern language are still missing: decomposition and abstraction. We won't write code for them today, instead we'll motivate them, and you'll see you've already been doing simple versions of both. Next lecture, we turn them into functions. Decomposition first. The idea is to take one large program and split it into smaller parts. Each part is self-contained, so the code in one doesn't interfere with the code in another, but they can still communicate, passing values back and forth. Take a single tangled block of spaghetti code, divide it into these independent pieces, and each piece solves one portion of the problem. Bring their results together at the end, and the whole problem is solved. Now abstraction. Once you've built a self-contained part and thought hard about how to make it work, nobody else needs to know how you did it. You hide the details behind an interface that says, "Give me these inputs and I'll hand you back an output." It's like a group project. Each person does their part. It doesn't matter whether they use the library or the internet. What matters is the result and knowing how to use it. You've already done a tiny version of decomposition. Picture a messy line that computes a circle's area. 3.14159 times 2.2 times 2.2. Pi matters and has many digits, and the radius 2.2 gets reused. Hard coding it invites typos, so decompose. Save pi in a variable, save the radius in a variable named r, then write area as pi times r times r. The messy line becomes clean. Reusable modules combine toward one goal. And you've already done a tiny version of abstraction too. Comments. Solve a problem set cleverly, come back a week later and the details are gone. But a one-line comment at the top say this uses bisection search, suppresses the details while reminding you what the code does. That's abstraction in miniature. Next lecture, we scale these up. Instead of copying and pasting the same code, which breaks when you fix one copy and forget another, we'll write small modules called functions. Write once, debug once, then reuse with different inputs for different outputs. Code that's easy to modify, maintain, and understand. We'll start with a real example, then dive into functions. To practice what you just learned, this course has free exercises and AI-graded feedback on ludium.ai. The link is in the description.